Welcome to solverfy.
In this problem, we have a glass surface coated with some material, and this coating has some thickness D. We're told it has an index of refraction of 1.25. The material the coating is made of has an index of refraction of 1.25, and I'm going to call that N1. And then we're told the glass has an index of refraction N2 of 1.5. So what's going to happen is light's going to come in from air here, left to right, and air has an index of refraction I'll call N0 of 1, and part of it's going to be reflected off of this first surface, and part of it's going to be transmitted and then reflected off of the second surface. We'll draw that in red. So that in total we have two reflected rays. And these rays are going to be, in general, they're going to end up phase shifted. And what the problem is asking is, what does this thickness D have to be such that these two red and black reflected waves come out 180 degrees out of phase? Right? So the black ray might be like this, and the red ray will be exactly 180 degrees out of phase, so that the net wave is zero, or has zero amplitude. So that means that the extra path that's traveled by the initially transmitted ray has to be some half multiple of the wavelength. Right? And so what's the extra path traveled? Well, it's once to the right and once to the left, so that's 2 times this thickness D. So we have 2D must equal some half multiple of the wavelength. So we can write that as lambda times and then m plus 1/2, where m is an integer. Now we have to be careful here because it's not actually lambda, the wavelength, but it's lambda sub n. I'm going to write it. Where lambda sub n is the wavelength in this material. So lambda sub n equals the vacuum wavelength divided by the index of refraction. And in our case, that's going to be N1. There's another thing you have to consider here, is that when light reflects off of a material with higher index of refraction, the reflected ray comes off 180 degrees out of phase, so an extra half wavelength. Right? So this black ray here, reflecting ray here, is going to get an 180 degrees phase shift, or half wavelength phase shift. But that's also going to happen on the second surface because it's again going from a lower index of refraction to a higher index of refraction. So we're going to have 2 half wavelength phase shifts, which is amounting to a full wavelength, right? 1/2 wavelength plus another half wavelength is a full wavelength, which is the same as no phase shift. So we actually, those 2 shifts cancel, so we can ignore them. But in general, you have to think about whether you have to include them or not. Now they want the minimum distance, which means we can set m to 0. So that's just, we only have this 1/2 here. So solving for D, we have that D will equal lambda n, which is lambda over n1 divided by 4, right? We have a 1/2 here, and then we have a 1/2 here from dividing by 2. And we're told that the vacuum wavelength is 600 nanometers. So plugging n1 and lambda into here, we get that the minimum thickness turns out to be 120 nanometers.